All right, hello. In this video, we're going to look at a certain type of situation with limits, something where we get what are called indeterminate forms. We've seen them before, but we've not used this word, and then see how to handle some of those with a new rule called L'Hopital's rule. So for an example, when we were looking back at specifically finding the derivative formula for the sine function, but we'll just say generally for trig functions, we encountered the following limit. So we were looking at the limit as x approaches 0 of sine of x over x. And just taking this on its own, this might be not might be, but it is a tricky one to figure out. You may remember that this limit was 1, or is 1, and we showed that and used that to help come up with that formula. But it was a little bit tricky. Using the limit laws, you might think, since these component functions, the sine function and then just that y equals x there, these are continuous, and so direct substitution would make sense, but of course the one problem where it wouldn't work, or the one point where it wouldn't work, is at 0, because there you get 0 in the denominator. But that direct substitution gives us 0 over 0, so it doesn't definitively say that the limit doesn't exist. We certainly don't know the limit does exist. We showed that it was 1, like we said, but at face value, you can't tell. So this is an example of what we're looking at, what are called indeterminate forms. So these have different types. The example that we have here is of, quote, type 0 over 0. So basically, if you were to do a direct substitution, what it would look like, that's the type. So it could be infinity over infinity. It could be infinity minus infinity. There's a lot of different types that we have. But for all of these, so the limit may or may not exist, but we can't evaluate it via direct substitution. So you have to come up with some other way of handling it. So like I said, here are some types. These are the types that we'll look at. You got 0 over 0, infinity over infinity, or minus infinity over infinity, or some plus or minus variation. These ones a little bit trickier, and these ones quite a bit trickier. So these last three, you've got some exponential expression type situations. Here you've got some just kind of weird arithmetic. 0 times infinity, it's not clear what that equals. It's not well defined. Infinity minus infinity, you might think, oh, it's just 0, but that's not entirely clear either. It's kind of a weird situation. So all of these are examples of indeterminate forms of different types. So we've seen things like this in the past. You might have seen something like this limit here. We didn't use the language indeterminate forms because we didn't have that, but it is an indeterminate form of type 0 over 0. If you do direct substitution, you get 4 minus 4 over, well, 4 minus 4, so 0 over 0. The way we would have tackled this in sections past, way back at the earlier parts of our calculus study, we use what we called cancellation property, and we found a common factor, the x minus 2, in both the numerator and denominator, and we said that these limits are the same, provided f of x equals g of x at every point except that point that you're approaching, then the limits are the same, and that's what we have here. So you can do that cancellation, and you get just a nice rational function there where 2 is in the domain of that. So you do a direct substitution, and you're in great shape. The limit is 2. Now, this approach won't work for all limits, unfortunately. But we've got something that's going to help us out in a lot of cases. This is something called L'Hopital's rule. So this is a rule that's to be used for indeterminate forms, limits that are indeterminate forms of a very specific type. It has to be type 0 over 0 or type infinity over infinity with the plus or minus. So here's what the rule tells us. We're going to suppose that f and g are differentiable and that g prime of x is not 0 on an open interval that contains a, except maybe at a. Weirdness probably happens at a. So a is the value that we're approaching. Now suppose that you've got an indeterminate form, that limit, of type 0 over 0 or plus or minus infinity over infinity. It's very important. Those are the only two types we can consider. Then that limit that we're trying to figure out, what we can do is look at the limit of the ratio of the rates of change. So look at the limit as x approaches a of f prime over g prime. If that limit on the right-hand side exists, then it turns out that the limit on the left-hand side exists and they equal the same thing. And if this is plus or minus infinity, then that original one is going to be plus or minus infinity as well. And this applies for one-sided limits, applies for limits at infinity. It's a nice rule. So we could have used this on the problem that we saw earlier that we could have tackled way back when, where we did that cancellation property. Instead, I could use L'Hopital's rule to get from here to here. The derivative of the numerator is 2x. Derivative of the denominator is 2x minus 2. Now I can look at this limit. Everything's good there. 2 is in the domain of that rational expression, so I just do a direct substitution. 2 times 2 over 4 minus 2. And I get 4 over 2, which is 2, which is what we saw the limit was earlier. Since this limit is 2, that means the original one by L'Hopital's rule is the same. It is 2. But we can also use this for problems where the cancellation property cannot be applied. So we don't have a comparable sort of thing to that very first limit that we talked about, the sine of x over x as x approaches 0. This is a kind of a classic case of using L'Hopital's rule. So this is type 0 over 0. So we're using L'Hopital's rule here. Derivative of sine of x is cosine of x. Derivative of x is 1. And that's good. That's nice and continuous. So you can just do a direct substitution, direct evaluation. Cosine of 0 is 1. And that's what we knew that limit to be way back when we were looking at the trig stuff, where we didn't have L'Hopital's rule. We had to do some other clever techniques to figure that out. Now it's a little bit easier. So this is a nice one. One thing to be careful about and to keep in mind, a common error is you're almost always going to have some expression like this where it's a quotient, something divided by something, and you might be tempted to use the quotient rule. That's a common error. We're not using the quotient rule here. We're not finding the derivative of this. We're looking at the derivative of the numerator over the derivative of the denominator. And that's important. So we've got many different types of indeterminate forms. L'Hopital's rule applies only to these two types. And for others, we may need to do some mathematical manipulation in order to set it up so that we could use the rule. Basically, rewrite it, be a little bit clever so that we get one of these two types. So for our first example here, get this expression. This is an indeterminate form, this limit. If you did a direct evaluation, you get infinity times sine of pi over infinity, which none of that makes sense, but sine of pi over a really large number that's getting bigger and bigger and bigger. This whole thing's approaching 0, so it would be like infinity times 0, which we usually just say 0 times infinity, of course. Or not of course, but we mean the same thing. It's the same type. So it's an indeterminate form. As it is, we can't use L'Hopital's rule. So what we do is we get a little bit clever and we rewrite it. And this is a completely crazy way to rewrite it. There's no good reason to do this except now we have type, well, we said this is approaching 0. This, as x goes infinity, this approaches 0. So now we have type 0 over 0, and we can use L'Hopital's rule. If you want to check that out, I'll leave it up to you, but that limit is pi. What I want to do here with the examples is just show how you can manipulate it to set it up so that you can use L'Hopital's rule. But remember, it needs to be type 0 over 0 or type infinity over infinity. One last quick example. Here's one where we've got some exponentiation going on. This is a little tricky. This is an indeterminate form. Again, this guy. And now it's of type 1 raised to the power infinity, which isn't a number. It doesn't make sense. Just like 0 over 0 doesn't make sense. But it's a type of situation that we can try to handle. So this one's even trickier than before. We can't apply L'Hopital's rule because it's not, so we cannot apply L'Hopital's rule. So it's not 0 over 0 or infinity over infinity. But the trick here is we're going to let that expression in our limit, we're going to call that y, and apply the logarithm to both sides. So I've got natural log of y equals natural log of this whole big mess. That x comes down in front, and I've got x times natural log of 1 plus 1 over x. Now this would be type infinity times 0, so that's not a number. We don't know what that is. But it's also not one where we could use L'Hopital's rule. So do that crazy thing like I did in that last slide, x times something, well, I think of it as, division by 1 over x. That's exactly what I've done here. So now this is type 0 over 0. Oh no. It should not have been there. Sorry for that typo. So type 0 over 0. And so now we can use L'Hopital's rule. One thing to be careful with, we look at the limit as x goes to infinity of this, and we found the limit of natural log y, so we have to do one extra step to find the limit of y. FYI, the limit is e, the number e, 2.7 da 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 da. So that's kind of interesting. The original limit. This limit is going to be 1, and that original limit is going to be e then. So that's L'Hopital's rule. Talk about, like I said, indeterminate forms. We've got a number of cases. To use L'Hopital's rule, remember, it needs to be 0 over 0, that type, or infinity over infinity. So you might have to do a little bit of manipulation. And then the other tricky part to keep in mind is that we don't use the quotient rule. We take the derivative of the numerator divided by the derivative of the denominator, looking at that ratio there, the limit of that. So a little bit tricky potentially just when you get started, but once you get the hang of it, like a lot of things, real slick to use and a real time saver. So that's it.